These worked example problems are associated with Module 4. We'll start by balancing this combustion reaction. So we have the equation written for us, but you know from lecture videos that I could just give you C3H8 and ask you to balance the combustion. So you know that it's reaction with O2 and you produce CO2 and H2O. So you could check just to start whether or not it's balanced to begin with. And this table is a nice way to set up that information if you would like to. So on the reactant side, I have 3 carbons, 8 hydrogens, and 2 oxygens. On the product side, I have 1 carbon, I have 2 hydrogens, and then I have oxygen in 2 different compounds, so I have to count it across all of them. I have a total of 3 oxygens, so we are unfortunately not balanced. For combustion reactions, remember that we balance things in a specific order. So we'll balance carbon first, and this can be achieved by putting a 3 in front of the CO2. Then we'll balance the hydrogens, which can be done by putting a 4 in front of the water. Then we will look at the number of oxygens we have on the product side, and we now have 6 from the CO2 plus 4 from water. So we have 10 total oxygens on the right-hand side, which we can balance by putting a 5 in front of the O2 on the reactant side. And this leaves a 1 in front of our C3H8, and we can check that each thing is balanced, again, using our table scenario, and in this case, it looks beautiful. So here's the summary for this problem. Let's do some practice with stoichiometry, also using a combustion reaction that has been balanced for you. The question we'd like to answer is how much carbon dioxide would be formed if 10 grams of C5H12 were completely burned in oxygen. We know the mass of the reactant that we're going to start with, and we're going to calculate the amount of one of the products that would be formed. Because we're starting with grams and our relationships are in moles, we need the molar mass of both of the things that we're working with. Because, it doesn't specify it here, and I would specify it in the problem, but you can tell from the way that the information is that we're going to go to grams of carbon dioxide when we report our product. So we're given the 10 grams of the starting material, but we'll need the molar mass of C5H12. And then if we want to go from moles of CO2 that we calculate to grams of CO2, we'll also need the molar mass of CO2. What we're looking at in terms of an overall strategy, we know the grams of C5H12. If we have its molar mass, we can convert to moles. And then the key part here, the concept that's super important from this part of the module, is that we can use the relationship between the coefficients in this balanced reaction to relate the number of moles that you would produce or that you would use up related to anything else within the reaction. So we get 5 moles of CO2 for every 1 mole of C5H12 that we react. And then we need the molar mass of CO2 if we want to report an answer in grams. So solving this, the molar mass of C5H12 is 72 grams per mole. So that's 1 mole on the top and 72 grams on the bottom to get grams to cancel. We have our conversion factor from the balanced reaction, 5 moles of CO2 for every 1 mole of C5H12. And the molar mass of CO2 is about 44 grams in 1 mole. So this time, the 44 is on the top so that we get an answer in grams, and the 1 mole of CO2 cancels with moles of CO2. So this reaction would produce 30.6 grams of carbon dioxide. And thinking about it, the magnitude of CO2 is about right, 1 to 5. and the units work. So this looks great. Here is the summary for this problem. So let's try something with limiting reactants. So we have 10 grams of methane, and it's burned in 20 grams of oxygen to produce carbon dioxide and water. And we're being asked first to determine what the limiting reactant is. So we need to start with a balanced chemical equation, and that is not given. So CH4, you would need to write that it reacts with oxygen to produce carbon dioxide and water, and then go through and add anything you need to balance it, which in this case is a 2 in front of H2O and a 2 in front of the O2. We also know the mass of the reactants, so we know how much CH4 and how much O2 we're starting with. The process that we need to go through involves relating things in moles, so we're going to need the molar masses, right? So we can convert the masses of the reactants to moles, which, and this says can, but we have to because the mole ratios are what's used to identify the limiting reactant. So 10 grams of CH4, that has a molar mass of 16.04 grams in 1 mole. So that would be 0.623 moles of CH4. 20 grams of O2, which has a molar mass of 31.999 grams, means that we have 0.625 moles of O2. The mole ratio is 2 moles of O2 for every 1 mole of CH4. So if we're looking at the number of moles of each reactant that we have, whenever I use 1 mole of CH4, I use up 2 moles of O2. So I'm really starting with almost identical numbers of moles. So my O2 is going to run out super fast because every time I take 1 CH4, let's say I take like 1 molecule from that pile, I'm taking 2 O2 from the O2 pile. And so the O2 will disappear more quickly. Now you can also, and the way that we've set up this strategy is take each of these mole amounts and calculate the amount of one of the products that you would make. And you should see that O2 makes the least amount of product. So we used the balanced equation and the fact that we started with the same number of moles, which frankly made it a little bit easier to kind of reason through that the oxygen would be used up twice as fast as the CH4. Because the moles were about the same, the oxygen would be used up first. So here's the summary for this problem. All right, let's take it a little bit further and do a percent yield. So what we're going to look at is aluminum burning in bromine to produce aluminum bromide. In the experiment we're looking at, we have 6 grams of aluminum reacted with an excess amount of bromine to yield 50.3 grams of aluminum bromide. Now, normally, with the percent yield problems, you have to first do a limiting reactant problem, but this just told you that the aluminum was the limiting reactant. It just did so by telling you that the bromine was the excess reactant, and then we don't even have an amount of bromine that was used because it frankly doesn't matter. There was just extra of it. So whatever amount we have, it's enough to react with more than 6.0 grams of aluminum. So that's all we need to know. So we have an initial amount of aluminum and we have the amount of product formed. We do need a balanced chemical reaction, but this is a case where we're given everything that we need. Now the word burns may be misleading, but if it doesn't say combustion, it's not that specific type of reaction we talked about. So it, for some reason, is just classified as burning. But we have aluminum reacting with bromine liquid. We do need to know that it's a Br2. It's one of our Brinkelhoffs. And then it produces aluminum bromide. So to put this ionic compound together, we do need to know that Br makes 1 minus anions and that aluminum makes plus 3 cations. Then we need to balance it. And now we have everything together that we'll need. So the grams of aluminum, if I have the molar mass, I can get to moles of aluminum. And then I can use my balanced reaction to figure out how many moles of aluminum bromide I would produce based on the amount of aluminum that I have. Once I figured out moles of aluminum bromide, if I use its molar mass, I can figure out how many grams of aluminum bromide I would produce in my happy perfect world. Right? This is going to calculate the theoretical yield of aluminum bromide. Then my percent yield will be what I actually got, so the 50.3 grams, divided by the theoretical and multiply by 100. So 6 grams of aluminum, the molar mass is 26.98 grams per mole. For my balanced reaction, I get 2 moles of aluminum bromide for every 2 moles of aluminum that I use. Then the molar mass of aluminum bromide is 266.7 grams per mole. So this would give me a theoretical yield of 59.3 grams of aluminum bromide. So my percent yield is 50.3 grams divided by 59.3 grams times 100, which is a percent yield of 84.8%, which is pretty good. Also, I'm going to go in and make this slide look a little bit nicer. In case I don't have the ability to edit this, there's a typo here from the textbook. This should say 2 moles of aluminum. So think about it. Well, we're under 100%, so that's pretty reasonable. All right, here's the summary from this slide. Again, this ratio, 2 moles of aluminum bromide, that should say 2 moles of aluminum on the bottom.